Welcome back to Chem 4300. In this video we're going to begin Chapter 18 on the electronic structure of the hydrogen atom. Now in an earlier chapter we learned how Louis de Broglie in 1923 proposed his matter-wave hypothesis. He imagined a particle moving through space as a wave packet. Now rumor has it soon afterward Erwin Schrödinger was giving a presentation on de Broglie's hypothesis of matter waves, and after the talk his colleague Peter Debye came up and said, well, if matter is acting like waves, then there must be some underlying wave equation to describe these waves moving through space. And of course we know now, soon after that, Schrödinger came up with his wave equation that was very successful in describing these waves. And that wave equation was published in 1926 in this paper, which in English is titled Quantization as a Problem of Proper Values. Now the paper was originally written in German. This is an English translation here of that paper. Now at the time the theories of the atom were mainly Bohr's theory and refinements by Sommerfeld, and in those models they required quantum numbers to get agreement with the discrete line spectra, the emission spectra of hydrogen atoms that were studied by Balmer and Rydberg. So these whole numbers were put into those theories, but with no explanation why they actually occur. And what Schrödinger finds, once he has his wave equation, is that those quantum numbers occur naturally in the solutions. And as he writes in his introduction here, he shows that the customary quantum conditions can be replaced by another postulate in which the notions of whole numbers, merely as such, is not introduced. Rather, when integralness does appear, it arises in the same natural way as it does in the case of the node numbers of a vibrating string. So it comes out naturally, as you know from our studies of the classical wave equation for waves that have boundary conditions and these standing waves appear. It's the same type of solution. So in his solution of the electron orbiting the positively charged nucleus, that boundary condition gave us the quantum numbers that we learn about in high school chemistry. Now, we're going to work through the solution for the hydrogen atom, for this electron bound to a positively charged nucleus. And we can do that analytically, although it's not going to be easy to do that. And we can see how it compares to the experimental measurements. Now, these analytical solutions will be the basis for looking at multi-electron atoms and even for looking at molecules, and particularly in those situations where we're not going to be able to find any type of analytical solution. This is going to be a challenging derivation, and I do not expect you to know how this was derived or be able to reproduce this derivation on your own, but I'm hoping that you'll be able to follow the derivation and see how these quantum numbers arise naturally. Those quantum numbers that you remember from high school chemistry, n, the principal quantum number, the azimuthal quantum number, the m sub l number, the m sub s number, all of those numbers are going to appear as we look at the hydrogen atom. Although the last one, the spin quantum number, is going to be a little tricky and is not sort of contained, doesn't fall out of Schrödinger's wave equation. So to start the problem, we were going to just think about what we have. Two particles, a proton and an electron, that are bound to each other, positively charged proton, a negatively charged electron, in some coordinate system. Now, we're going to take this system of two particles and we're going to write this in terms of the center of mass, write the whole equation in terms of the center of mass. So we're going to write down the total mass of m for the proton and mass for the proton and electron added together. Then we have the center of mass term, and then here we have the relative distance between the electron and the proton. So we're looking at the relative motion of the electron and the proton in the end here. So we're going to express these two vectors for the proton and the electron in terms of the center of mass and this relative distance between them. The kinetic energy for those two particles, the proton and electron, are here, and if we rewrite them in terms of these other coordinates, then they have this form here, where we have the rate of change, the speed of the center of mass, and then we have this term here related to the relative motion of the two particles for their momentum here and here. Now, if I go back to the total energy with the kinetic energy term and the potential energy term and use those expressions, so I'm going to plug in those expressions for in terms of the center of mass and the relative position of the two particles, then it comes to this form here, where now the mu is the reduced mass for the proton and the electron. So now we can see that we can define two new momentums. So we have the momentum of the center of mass and the momentum associated with the relative motion of the two particles. And that then allows us to take the total energy written in terms of the center of mass and their relative motion, and we're going to have the translational energy of the whole atom and then the internal motion here in this second term. When we translate this into quantum mechanics, then obviously we're going to turn these momentum quantities into operators, and so these guys become here and here become these terms here with the gradient operator involving the center of mass and the gradient operator involving the relative distance between the two particles. This is our total wave equation for that system. Now we're going to, and this is our wave function here, so now what we're going to do is we're going to make a proposal for a solution, which is that the wave function will be a product of a part that depends only on the center of mass and a part that depends only on the relative motion of the two particles. So we'll take this guess, we'll plug it into our wave equation, and when you do that, and I'll leave out the steps here because we've done this many times, you find that you can break it up into two differential equations where they're decoupled. This is a differential equation describing just the motion of the center of mass, which is just a free particle in a sense, and then this is the motion of the relative motion of the electron and the nucleus. And the total energy from this equation and from this equation gives us the total energy for the whole system here. So this is the equation that we're going to solve. The most important is that this potential here will be the Coulombic interaction, the attraction between the electron and the proton. And that's sort of the beginning of this problem. We're just setting it up. We're separating out the motion of the center of mass from the relative motion and focusing in on solving this version of the Schrodinger wave equation to get the eigenstates and eigenvalues for the hydrogen atom. So the next thing we're going to do is we're going to look at the symmetry of the problem, which is a very spherically symmetric problem. The Coulombic interaction is a conservative central force. So we're going to turn this potential energy term in terms of spherical coordinates, and that will be the topic of the next video.